This is Mr. Lee. In this video here, we're going to look at the center of mass, but we're going to start off with the algebra version, and then we're going to go straight into the calculus version. So if you're not in the calculus-based course, you could just pay attention all the way up to the algebra version. So let's begin. What this video is looking to do is try to determine the location of the center of mass. Okay, so it's a little bit more intricate than just looking at the object and trying to figure out where the average is. I mean, you can do that if it's like in a one-dimensional, like along the x-axis or along the y-axis. But things do shift when we look at both the x and the y-axis. All right, so let's just start off with the formula. So the formula for the location of the center of mass is the position of the object times the mass of the object, right? And this is a summation. So this is all of the masses, the individual mass times its individual position, okay, over the total mass overall. Okay, so that formula looks a little bit complicated, but when we do our example, I'll show you exactly how to break that down. All right, and the calculus version will look something like this. So it's a summation of all of the masses at a certain location over the summation of the individual masses itself. All right, so let's do an example problem. So let's say we have a bar. Let's say this bar has a mass of 3 kilograms, and this bar has a object of m, and it is located a distance of, let's say, -1 meters down. Right? I'll show you exactly why we can call that -1. And we have an object here that is an object of, let's say, we'll say it's 2m, right? It's 2m, and it's located a distance of -2m down. And so the question here is, where is the system's center of mass, assuming that this entire thing is the system. And the reason why I drew the strings, right? So this is like a ball being hung from like a little stick. The reason why I drew the string as dots is because we want to make sure that the string is massless in this situation. Because if the string also has a mass, we need to find the center of mass of the string as well. And that just complicates things for this example video. All right, so the first thing that you want to do is you want to create a coordinate system, and in that coordinate system, you want to be able to locate each individual objects and represent them as dots. So with that image there, I'm going to do it off on the right-hand side, but you can do it right below it. Okay, this initial dot, this will be my 0, 0 point. So I like to put an object at the origin. It's entirely up to you where you make your origin. But for this example problem, this is my 3m, and it's located at 0, 0. Okay. And let's see here. We'll make the length of this here. We'll make it nice and simple. This has a total length of 4 meters. All right. So if the center of mass of the rod is right here in the middle, okay, and represented that over here with the black dot, we can say that 2 meters to the left and 1 meter down is that 1m object, and I'll represent that with this red dot here. Okay, so if I were to go back to my coordinate system, it'll be 2 to the left and then 1 down. So this is where my 1m is located, and this object is located at -2, -1. All right, now let's do the same thing, but for the other object. So the other object, I'll do this in blue. We can see that it is 2 over and 2 down. All right, so this is +2, and this is -2 for the -2m object. So here we have +2, and then we can go down, 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 and this is where the 2m object is located. So this was 2m, and so this is +2 and -2 in my coordinate system. So the question becomes, okay, if I were to get rid of all those dots, right, you can keep them if you want, but I just want to clean it up a little bit. The problem now becomes, where is the center of mass if this is my system, right? And so we could make an educated guess, but with the formula, we don't have to make that educated guess. We got to find out exactly where the center of mass is located. And so in order to do that, if we take a look at our formula, I'm going to write down the formula. We say that it is summation of xm all divided by the total masses. So the denominator is actually the easy part, right? The denominator just means that we have to add up all the masses together. So we have 3m plus 1m plus 2m, right? And so that just becomes a total of 6 in the denominator, right? So 6 kilograms. And so the center mass has a mass of 6 kilograms, but now we need to know exact location. So this is where things get tricky. You see how here we have the x and y axis? You have to use this formula for both the x and the y axis. So I'm going to do the x axis first, okay? And I'm going to go in this order. I'm going to go object 1, object 2, and then object 3. So we can say object 1 has a mass of 3, and it is located at position 0. So it'll be 3 times 0, okay? And what this symbol means is a summation, so we need to add up all the masses and the locations together. So the next object, therefore, becomes object 2, which has a mass of 1, times the x location, which is -2, okay? Plus the final object, which is an object of 2m with the location of 2. So in the x coordinate system, we have 3 times 0, which gives us 0, plus 1 times -2, which is -2, plus 2 times +2, which is 4, all divided by 6. So this is 2 over 6. Okay. All right. So the x position would be 1/3. All right. Now what about the y? So we're going to do the same thing with the y. Okay. I'm going to show you the math. The y, I'm going to start off with the 3 object first as a coordinate of 0 plus object 2, which is a mass of 1 times -1. Okay, that's a multiplication symbol. Plus 2 times -2, all divided by 6. So this gives us 0, I'll put it above, -1, and then -4. So the total is -5 over 6. So the y coordinate will be at -5, 6. And so if we were to create a coordinate here, we would say the center of mass is at 1/3 and 5, 6. And so if I were to do my best guess, right, so 1/3 in the x direction, if this from here to here is 2, so a third would be like here, right? That's like 1/3 right there, and it'll go down 5, 6, which is almost 1. So like right around here, all right? And so at this point right here is our center of mass. It kind of makes sense, right? So this center of mass is like a good average distance between the 3 objects, and the coordinate for that one is 1/3 and -5, 6. All right, so that's how we do it in the algebraic fashion. But now I'm going to show you exactly how to do this for the calculus version. So the calculus version, it's taking the same idea that we did before, but the method from before is used for a uniform distributed object, meaning it's like a bar and it's like uniform density. So uniform density simply means that this bar is made up of the same material, such as steel or such as plastic, right? And the density throughout this entire thing is even. So because it's even, we could just say that the center of mass for this object is right there in the middle. But in the real world, this isn't the case. And the classic example here is like a corn dog, right? So a corn dog has like a wooden stick, and then we have like the middle hot dog portion, and then surrounding the hot dog we have the cornbread, right? So the cornbread. So with a corn dog, it's not uniformly distributed with the same density because it's made up of different materials. Okay, and so it could be something like that, or we could have like a baseball bat, right? So a baseball bat kind of does like one of this, and so the center of mass would be geared towards the more massive end. Okay, so we would use the calculus versions when things are not uniform. So the idea here is we're going to do an example with a bar. Right? So this is a non-uniformly distributed mass bar. So what this shows us is we are looking at a tiny bit of mass. Okay, so that's our dm, and we want to know like in this tiny chunk, right? So that's the x distance away from wherever. So we could set the coordinate plane like this. So this distance away x, okay, how much mass do we have that tiny chunk? Versus, let's say, out here, for this tiny chunk, which is at a distance x away, right? How much mass does this tiny chunk have? Okay, and so the center of mass takes a look at all those individual tiny chunks and see where the center of mass is located. So for linear density, okay, there's a special formula, okay, and the formula for linear density is usually that Greek letter is lambda, and the formula is dm over dx, which shows you a tiny amount of mass per tiny distance. Okay. So this is for a linear density, so an object with a straight line. And we'll look at different types of densities as the course progresses. So if we know, like this is an example problem, if we know that the lambda, the function of lambda is like say bx squared, right? So in a problem, they will tell you that you have like a rod of non-uniform, so non-uniform linear density. Okay, so they tell you that you have an object, it's a rod, and it's a non-uniform linear density, and they give you this function here. And they ask you, where is the center of mass? So in order to solve this, what we have to do is we have to use a little bit of calculus. So let's begin. So we know that lambda is equal to dm over dx, and the function that we have is bx squared, where in this case b would just be a constant. So if we were to do a separation of variables, so dm is equal to bx squared times dx, and you want this x squared and this dx close together because those are the same variables that we're looking at. Okay, and look what we just did. We just separated a derivative function. So what we can do to go to I guess finish the calculus of it, right? The separation of the derivative. We're just simply taking the integral. We can see here that the integral of this, right, the integral of dm is equal to the integral of bx squared with respect to dx. So remember that b is a constant, so we can take it out. And so it's just the integral of x squared dx. And let's say the rod has a length of L, capital L. Okay. And so here, if we take the integral, we will get b x cubed over 3 from 0 to L, and that is the integral of dm. And so if we were to plug in that L, we will get bl cubed over 3, which is equal to this. Now, the reason why I want to keep it in this form, not go any further, is this right here is part of the center of mass formula, which I'm going to write over here. So the center of mass formula, this is our denominator, right? So this becomes our substitution. So bl cubed over 3. And now, for that numerator just simply shows us that we got to go through the same process, except what we want to do is we want to multiply a x in front of it. So what that means is that we know that rho is equal to dm over dx, okay? And we know that this is rho dx is equal to dm. But what we want is we want an x in front of that dm. So I'm going to multiply both sides by that x. Okay, and so well, remember the rules of mass don't apply. Whatever you do to one side, you have to do to the other. So this becomes x. Where is it? Bx squared, which is my substitution. Dx is equal to x dm. Now we can integrate it. So with this, the algebra becomes bx cubed. So still taking the integral dx is equal to the integral of x dm. Remember that x dm is our numerator. So at this point, we are still going from 0 to L. So if we take the integral of that, we get bx to the fourth divided by 4, and we're going from 0 to L is equal to the integral of x dm. And so this becomes bl to the fourth all over 4. And this is our numerator. So I'm going to plug that in, bl to the fourth over 4. And so we have something that looks like this. But if we start to simplify things, this b cancels out, L over 4 and L over 3, right? That just leaves us with a L. And that 3 on the bottom, because it's in the denominator, it rises up to the numerator. And so our final answer becomes 3/4 L. So what this shows us is that the center of mass is 3/4 of the way. So if this is the bar, and it goes from 0 to L, the center of mass would be, according to this function, 75% of the way. So the center of mass would be located right there. All right, we'll get more practice with this in class. See you next time. Bye-bye.